In this video, we're going to put together what we've learned into some examples in an application. Now, in the first couple of examples in this video, you're going to need how to find the x-intercepts on your graphing calculator, and I've included a separate video for that at the end of this lesson. So if you don't know how to find x-intercepts on your calculator, make sure that you watch that video and take a couple notes on how to do that. Okay, now in this first couple of examples, it says graph each polynomial function using your calculator, and based on the graph, determine the intercepts and the end behavior. So when we look at this first function, I'm just drawing a sketch of what I see on my calculator. What I'm seeing on my calculator when I graph this, now I'm a horrible artist, so please bear with me. It looks something like this, and it dips pretty far down, and then it comes back up. So it looks something like this. So to kind of put everything together, if you notice, we've got two turning points. So the smallest degree of this polynomial would be 3. The least degree would be 3. And if you notice the equation of our polynomial, that fits, because if I were to multiply that all out, that would be an x cubed polynomial, because I have 3 x's there. And when I multiply the x times the negative 2x times the negative 2x, that would give me an x cubed term. So putting that together, then also putting together our x-intercepts. The x-intercepts are the value of x when y is 0, so I would plug in 0 for y, and I would solve this for x. If I set each of those, since it's already factored, if I set each of those factors equal to 0 and make my little mini equations, I would get my x-intercepts to be x is 0. Let's see, that would be 5 and 1. And when I look at my graph on the calculator, that's exactly where it crosses the x-axis. x0, here's 1, and this would be where it crosses at 5. Now the end behavior, if I look at my arrows are in the first and the third quadrant. So I would say, as x goes to positive infinity, y would go to positive infinity, because this arrow right here in the first quadrant means I'm going to the right and up forever. And then the arrow that's in the third quadrant is telling me as x goes to negative infinity, y is going to negative infinity. So we identified our turning points and saw how it matched up with the degree. We identified our x-intercepts and our end behavior. Now, if we look at the graph of this second function, what it looks like when you look at this, it looks like a quadratic, a really skinny quadratic, a smile shape, but it dips all the way down to 625, negative 625 on the y-axis. It's x to the fourth, which looks like a skinny quadratic, and it's been bumped down to 625. It's been shifted down. So if I were to go ahead and factor that, I would get x squared plus 25 and x squared minus 25, because it's the difference of squares, so I can factor it as the difference of squares. 25 times 25 would give me the 625. This is the sum of squares, and I can't factor that anymore over the reals. So this is going to yield no real solution. But this, however, I can factor again and break that down into x plus 5 and x minus 5, which would give me two x-intercepts at plus and minus 5. And if you look at your graph on your calculator, that's exactly where it crosses. at -5 and +5. So our x-intercepts are +5 and -5. If you look at the number of turning points that we have one turning point. So that means the smallest degree that this polynomial could be would be degree 2. However, it could be a degree more than that. And if, as you see, this is a degree 4. And then the last thing would be our end behavior. So my arrows are in the first and second quadrant. So that tells me for the arrow in the first quadrant, as x goes to positive infinity, y would go to positive infinity. And for the arrow in the second quadrant, that would mean as x goes to negative infinity, y is still going to positive infinity. So the arrows are both pointing up. So even though you're going out right and left in both directions, y is still going up. Okay, now the last problem in this section is I want to go over an application with you on how we can use polynomials to set up an application. So it says an open box is to be constructed by cutting out square corners of an x-inch side from a piece of cardboard that is 14 inches by 14 inches. And then we fold up the sides. And we want to express the volume of the box as a function of x. This is a little bit hard to visualize, but if you have a scratch piece of paper in front of you that you don't mind tearing up, it might be worth your while to kind of follow along what I'm doing with an actual piece of paper and imagine that you're actually creating this box. So it says here that we have a piece of cardboard that's 14 inches by 14 inches. So here's my cardboard that's 14 inches by 14 inches. Now it says you take out corners that are x inch. So they're not telling you the size, they're calling that x. So if I cut out a corner here, a corner here, a corner here, and a corner here that is x by x, so maybe x is 1 inch. I don't know. That's what we're trying to set up here. So if I imagine that I cut those corners out, and then that would make the bottom of my box to be this right here. Because when I take out that corner, I'm going to fold it up. And this now becomes my side. This becomes my side. So I've got my 4 sides here that get folded up. And this is now the bottom of my box. So now, let's see if I can draw this. I've got a box that looks like this. This was from where this is going to be height x because that's where it was cut out, that corner. And this is going to be height x as well. And this length here and here is going to be 14 minus 2x because this whole length from here was 14. And then I cut out an x over here and an x on this side. So I'm taking out 2x for that length to create this whole side right here. So this whole side right here is 14x, or 14 minus 2x, and this is 14 minus 2x. So when we go to create a formula that illustrates the volume of this box, remember volume, we'll call it V of x for volume. Volume is the height times the length times the width. The height of this box is x. The length and the width of this box is both 14 minus 2x. So this polynomial right here is going to represent the volume of this box when we cut out those squares and we fold up those sides. This will be the volume of the box. So now I can plug in different values of x to see what would give me, what value of X, what inch, would 2 inches give me a maximum volume, or would 3 inches give me a maximum volume? So I can start plugging in values for that X to determine the volume of the box.